This conversation is powered by Google Illuminate. Check out illuminate.google.com for more. Welcome to this discussion on the Variational Lossy Autoencoder, VLAE, a fascinating approach to representation learning. The paper details a method combining variational autoencoders, VAEs, with autoregressive models. Let's start with the core idea. What problem does the VLAE aim to solve?
The VLAE addresses the limitations of traditional VAEs in learning disentangled representations, particularly for complex data like images. Standard VAEs often struggle to separate global structure from irrelevant details like texture. The VLAE tackles this by incorporating autoregressive models, allowing for controlled information loss, and a focus on learning specific aspects of the data.
The paper highlights that VAEs don't always auto-encode, meaning perfectly reconstruct the input. Can you elaborate on the conditions under which this occurs and why this is relevant to the VLAE?
A VAE's ability to autoencode depends heavily on the expressiveness of its decoder, PMGXEC. If the decoder is powerful enough, like an autoregressive model, it can model the data distribution, PEX, without relying on the latent code Z. This is explained through the bits-back coding perspective. The model prioritizes efficient coding, and if the decoder can capture all the information locally, it won't use the latent code. The VLAE leverages this information preference to control what information is encoded in Z.
The bits-back coding perspective is crucial here. Can you explain how it relates to the VAE's objective function and the choice of decoder?
Bits-back coding views the VAE as an efficient coding scheme. The objective is to minimize the expected code length, which is related to the variational lower bound. The decoder's expressiveness directly impacts this efficiency. A powerful decoder can potentially model the data without the latent code, leading to a lossy representation where only the information not captured by the decoder is encoded in Z.
The paper proposes two key improvements to the VAE architecture. First, the use of a lossy code via explicit information placement. How is this achieved?
The lossy code is created by designing a decoder with limited capacity to model certain aspects of the data. For example, using a pixel CNN with a small receptive field restricts the decoder's ability to capture fine details like texture. This forces the VAE to encode this information in the latent code Z, resulting in a lossy representation focused on global structure.
And the second improvement involves the use of an autoregressive flow, A for the prior distribution P, eddy. What's the advantage of this approach?
Using an AF prior is equivalent to using an inverse autoregressive flow, IAF, posterior, which improves the efficiency of bits-back coding by reducing the Nello divergence between the approximate and true posteriors. Crucially, the AF prior offers this improvement without increasing the computational cost during training, making the model more expressive.
The experimental results are quite compelling. Can you summarize the key findings across different datasets?
The VLAE achieved state-of-the-art results on several binary image datasets, MNIST, Omniglot, Caltech 101 silhouettes, demonstrating improved density estimation compared to existing VAEs. On CFAR-10, it achieved competitive results, outperforming many variational models and showing the potential for handling natural images. The experiments also confirmed that the VLAE successfully learns lossy codes that prioritize global structure.
The paper also explores the impact of the pixel CNN decoder's receptive field size on the learned representations. What insights did this analysis provide?
Varying the receptive field size showed a trade-off between detail preservation and global structure capture. Smaller receptive fields led to latent codes that retained more detailed shape information, while larger receptive fields resulted in codes focusing on coarser global structures. This highlights the flexibility of the VLAE in controlling the type of information encoded in the latent representation.
The paper mentions several related works. How does the VLAE differentiate itself from these existing approaches?
While other works have explored combining VAEs with autoregressive models or using autoregressive flows, the VLAE uniquely combines both techniques and provides a principled framework for controlling information loss through the decoder's architecture. The bits-back coding analysis offers a novel perspective on why and how the latent code is used, guiding the design of the lossy representation.
Finally, what are some potential future directions for research based on this work?
Extending the VLAE to other data types, particularly temporal data like audio and video, is a promising avenue. Another direction is to design latent representations tailored for specific downstream tasks, potentially improving semi-supervised learning. Further investigation into the optimal design of decoders for different data types and tasks is also warranted.
This has been a very insightful discussion. Thank you for explaining the intricacies of the variational lossy autoencoder.